So our lesson on 1.7 is about solving absolute value equations and inequalities. So we're still going to be solving equations or solving inequalities, but this time we're also going to have the aspect of absolute values playing into our solution. So first thing I want you to think about is what absolute value truly means. And we know it's the bars, and we know that from Algebra 1 usually meant to make things positive if they weren't always positive. But the reason things were always positive inside the absolute value bars is because it really means distance from 0. So the absolute value of 4 is 4 units, but the absolute value of -4 was also 4 units because either direction it was still 4 units away. So in algebra, when you have the absolute value of x equals 5, that means the x, the stuff inside the bars, could be 5 or it could be -5, and that's the kind of gist of what's going to happen today. So first, 2x minus 5 equals 9. Well, the stuff inside the bars, the 2x minus 5, it could technically equal 9. It could also technically equal -9. So this is going to give us two solutions, both of which are correct. And we're just going to solve them. So 2x minus 5 equals 9. We're going to add the 5 to both sides. So we get one answer of x equals 7. And the other answer of -2. Now both answers are correct. Neither one's more correct than the other. We're just kind of done. So the thing to think about on those problems when it's an absolute value equation is that you must set up both problems. Now when it's an absolute value inequality, not only do you have to negate the answer, but we're going to have to take that the inequality symbol, we're going to have to flip it. So we're going to negate the answer, make it negative, and we're going to have to flip the sign. Now the other thing I want you to write down really big on your notes somewhere is that less than problems are always and problems, and greater than problems are or problems. If you remember back from lesson 1.6, the graphs of ands and ors looked very, very different. Ands were in between the two numbers, and ors graphed outside of the two numbers generally, and we're going to see that happen. So on our example, 2x plus 7, absolute value of that is less than 11. The first problem, you just take off the bars, but then for the second problem, we flipped the sign, made it a greater than, and then we negated the 11, made it a -11. So we're going to go ahead and solve. We're going to subtract 7 from both sides. So we get x is less than 2, and if I subtract 7 here, we get x is greater than -9. And now we're going to have to graph this. I don't really care if you count out all the values. You can kind of fudge it. I really don't mind. -9 would be down here, and +2 would be somewhere up here. And then because these do not have equal symbols under them, they're both going to be parentheses. And remember, and problems are the restrictive problems where you shade in between. They both have to be true. So greater than -9 and less than 2. So that's how we graph that. Now, let's back up a step. We also need to write the interval for this. And remember, the interval starts from the left and travels to the right. So the interval for the solution starts at -9 and travels all the way up to 2. And again, I know this looks like an ordered pair, but the answer is not an ordered pair. We're using the context of the problem, and I understand that -9, 2 in parentheses is really an interval. Okay, the next problem is originally a greater than problem, which makes this an or. So we set up our two problems. 3x minus 2 is greater than or equal to 8, or, that was just the bars taken off, 3x minus 2 could also be less than or equal to a -8. We flipped the sign and we negated the answer. Now notice we'd never ever change anything inside the bars. That always stays the same. So 3x, we're going to add the 2, and then divide by 3. Now, this is a case where I really would probably prefer a decimal just because I have to graph it. So I'm going to round that to x is greater than or equal to 3.3. For my next problem, I'm going to add the 2, and then divide by 3, excuse me. I get x is less than or equal to -2. So again, I'm going to kind of fudge it. Somewhere here. And if I want to graph everything greater than or equal to negative 3.3, that's that way. Or anything less than or equal to negative 2, that'd be everything this way. Brackets on both because of the equal to bars, and ors usually shade out to the side, so that's what I see. Okay, the next example, because it's a greater than symbol, this is going to become an or problem. So our first problem is 4x plus 10 greater than 2, or the next problem could be 4x plus 10 is less than, and then negate negative 2. So we're going to go ahead and solve. We're going to subtract 10 from both sides. 4x greater than negative 8, so x could be greater than negative 2. And for my next problem, 4x less than negative 12, so x could be less than negative 3. So I'm going to have to graph everything that is greater than negative 2 or anything less than negative 3. I'm going to go ahead and put these down on the number line. Less than negative 3 would be everything this way. Greater than negative 2 would be everything this way. And notice I have parentheses on both of those because it's not equal to. Now my interval for that solution is going to go from negative infinity up to negative 3, parenthesis, and then it's going to jump to negative 2 and then go forever to infinity. Oops, I don't think I ever did my interval for this guy. Let's back up to part C. Negative infinity to negative 2, bracket, union, bracket, 3.3 roughly to infinity. Now if you wanted to keep the 3.3 as a decimal, that's fine. It's just kind of weird for this type of a problem. Okay, letter B is going to be another greater than, so it's another or. So we have 2x plus 3 greater than or equal to 11, or 2x plus 3 is less than or equal to a negative 11. I flipped the sign and I negated the answer. So we're going to go ahead and subtract 3. So we get x is greater than or equal to 4, or x is less than or equal to negative 7. So again, don't have enough lines. I'm just going to kind of fudge this. Here's negative 7, and let's pretend here's 4. So if I want to show everything greater than or equal to negative 4, or anything less than or equal to negative 7, I show that. And now when I write my interval solution, reading left to right, I go negative infinity to negative 7, bracket, and then it jumps all the way up to a 4 to infinity. Okay, the next problem, you notice, doesn't have any graph because this is no longer an inequality, this is an equation. So these were a little more simple to solve just because we don't have to think about so much. You're still going to set up two problems. 2 minus 4x equals 10. And then the other problem, remember, keep the inside stuff the same, but you negate the answer. So it could equal 10 or negative 10. We're going to subtract 2 from both sides. We get negative 4x equals 8. So one answer is negative 2. And then the other answer would be positive 3. There's no need for a graph because we don't have intervals when we're just solving equations. Okay, this is a less than problem, so remember these are and problems, so it's important you write down the and. So it's less than or equal to 21, and 4x minus 9 is, flip it, greater than or equal to a negative 21. So I'm going to go ahead and add the 9 to both sides. And again, we have a fraction technically. I'd prefer a decimal on this problem. So x has to be less than or equal to 7.5. And let's see here. X must be greater than or equal to negative 3. So when I go to graph this, I got to show everything that is greater than or equal to negative 3 and less than or equal to 7.5. So you know I'm going to kind of fudge where these are located. greater than or equal to negative 3 and less than or equal to 7.5. And remember, and problems shade in between, and that's exactly what we see here. So our interval for this solution goes from negative 3 up to 7.5. And our last example has the absolute value of negative x plus 5 greater than 6. Now remember, you don't ever change what's inside the bars. You only change what's outside of the inequality. So we have negative x plus 5 is greater than 6. Since it's greater than, this is an OR problem. Negative x plus 5, flip the sign, is less than, and then negate the answer, a negative 6. So negative x is greater than 1. And then be careful, remember our rule, when we divide by a negative number, you need to flip your symbol. So here we have negative x less than negative 11. And again, divide by a negative, so we need to flip our symbol. So I got to graph everything that's less than negative 1 or anything greater than 11. And again, I don't have enough lines here, so I'm going to fudge it. These are parentheses. And no surprise here, because it's an OR, we're going to end up shading the outsides like that. So for our interval for our solution, it goes from negative infinity to negative 1, parenthesis, and then it jumps all the way to 11 and goes to infinity. Nice job. That concludes our lesson on 1.7.